Now we will study the reaction of ethers. First is the dehydration of alcohols. If we dehydrate it with a very high temperature, like around 443 Kelvin, in sulfuric acid we'll get an alkene. But if we heat it with a less than 443, around 413 Kelvin, then we will get an ether. Then what is the mechanism? Let us see the mechanism. First, you know that alcohol's oxygen has a lone pair. This lone pair will attack the H plus available from H2SO4 and it will combine like this. Now, as soon as oxygen gets a positive charge, it takes the electrons from this bond between CH2 and oxygen towards it and breaks from over here, giving a positive charge over here, and hence one more alcohol is there which is having a lone pair. This alcohol attacks to this carbon and hence the product form is this. And as oxygen is having a plus charge and oxygen never ever takes the plus charge on it, it always try to take a lone pair from the surrounding bond and give the H plus to other atoms. So therefore it takes the H lone pair from this bond, OH bond, and gives out H plus and hence forms a ether. And SN2 is suitable method only for 1 degree alcohols. Means this mechanism follows SN2 reaction and it is only suitable for forming ethers from 1 degree alcohols. Now Williamson synthesis. We use here RX alkyl halide with RONA and it gives us ROR dash plus NaX. And better results of this are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution and hence there is more elimination and an alkene is formed rather than getting an ether. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. This is what I said earlier. Now the cleavage of CO bond in ethers. Now ROR is reacted with HX, it forms RX plus ROH, and if we again react with alcohol with HX, or if in this step we have excess of HX, it forms RX plus H2O. Similarly, PHOR reacts with HX to form phenol and alkyl halide, and ROR dash unsymmetrical ether also undergo HX to form RX plus R dash OH. So the order of reactivity of hydrogen halides is as follow. HI has the maximum, then HBr, then HCl. The cleavage of ethers take place with concentrated HI and HBr at high temperature only. If the temperature is low, it will not follow this reaction. Now proceeding with the reactions of phenol. When a phenol is reacted with dilute HNO3, a mixture of orthonitrophenol and para-nitrophenol is formed, and we know that ortho and para isomers can be separated by steam distillation, and the fact due to this exists is that this causes intramolecular hydrogen bonding, and this intermolecular hydrogen bonding. Therefore, boiling point of this compound is higher than boiling point of its corresponding orthonitrophenol. Moreover, when we react phenol with a concentrated nitric acid, it forms picric acid, which is the common name of this compound, that is 2,4,6-trinitrophenol. And I am putting an emphasis that you should learn as many as common names as possible, because there are many questions in which you will know each and everything, you will know the mechanism and all, but if you don't know the common names, then you will not be able to solve. So you should know them. Then again, for getting only a one product, that is here as we are getting this around a ratio of 53% to 47%, and hence there is no something like major or minor in this. So if we want something major, like if we want a para isomer to be major, we use Br2 in CS2 at 273 Kelvin. It is the room temperature. In this we get the para isomer as to be a major compound. Then when phenol is treated with bromine water, 2,4,6 tribromophenol is formed and it is white precipitate. You should remember that it's a white precipitate because this is what differentiates phenol. Then we have the coal-based reaction, in which phenol is first reacted with NaOH to form phenoxide ion. Then it is reacted with carbon dioxide and then with acidic medium to form 2-hydroxybenzoic acid, also known as salicylic acid. Finally, the most typical reaction of phenol is Riemann-Tiemann reaction, in which the most common, we can also say, and widely asked reaction, and a very important one, in which a phenol is reacted with CaCl3 and aqueous NaOH, and then it forms a carbene as an intermediate, and following the carbene mechanism it adds, and this is the intermediate which we get. And then when we add NaOH, it forms aldehyde group over here, and finally when we add it into acidic mixture, we get an aldehyde which is salicylaldehyde. Finally, when phenol is reacted with zinc, dust, it becomes benzene and we get ZNO. Basically it reduces phenol into benzene. Then in oxidation reaction we get, when phenol is reacted with sodium dichromate in acidic medium, we get a benzoquinone. And let us see what is a Gutermann reaction. In Gutermann's reaction, HCl is first added with HCN, which is a cyanide group. It is also known as hydrogen cyanide in presence of AlCl3, aluminium chloride, to form ScNaCl, and you can see how it is written. And then when this is reacted in presence of AlCl3 and HCl, we get imine, in which CH double bond NH is attached over here and phenol is there and is attached to a para position. And then when we hydrolyze it, we get a aldehyde instead of an amine, which is para hydroxybenzaldehyde.
Hello everyone. Now since we have completed all the important theoretical concepts from the chapter Alchols, we'll now be switching over directly to the problems. In question number 1, as you can see on your screens, a reactant is given to us and it is treated with 3 different reagents under 3 different conditions, and we need to predict the product that will be formed in each case. So let us see the approach which is to be followed in these type of questions.
Now we proceed with the first question, and you can see different varieties of the first questions. In the first question there are different varieties, like here in LiAlH4, the second step we have used deuterated hydrogen.
Okay.
In the second question, second part, B part, they have used LiAlD4 and H2O, and the third part they have used NaBH4. So basic approach to solve this type of question is that you should go with mechanism.
Okay.
Because once you go with mechanism, the things become too easy. You don't need to memorize any reaction, or you don't need to focus on rote learning.
Okay.
Just by mechanism you can do it. So let us proceed. Let us proceed with the general mechanism of any aldehyde if it's reduced with an LiLH4.
Okay.
So let us take the most simple case in which aldehyde is there.
Fine.
We are reacting it with LiAlH4.
Okay.
We know that Al is plus 3, Li is plus 1, and therefore hydrogen has a -1 oxidation state, so total is -4.
Okay, right.
And the solvent over here is ether. As we know that ether is inert, therefore it will not react with LiLH4.
Okay.
Now we know that in aldehyde the CO bond is slightly polar,
Yeah.
and we get a del minus charge on oxygen and del plus charge on carbon.
Right.
So when LiLH4 approaches it, it splits into LiAlS3
Okay.
plus H minus, and this H minus reacts over here because it's having a delta plus charge.
Okay.
So it's then, and this LiAlS3 goes towards the oxygen.
Okay.
Therefore, the compound form is RCOLiAlS3 hydrogen.
Okay, so this is the intermediate compound which is formed.
Yeah, this is the intermediate compound. Similarly, the lithium aluminum hydride now has 3 more H minus.
Which it can donate.
So it will again react with 3 more aldehyde group.
Okay.
And finally it will form a compound like this. And then, as in this case we are dealing with the second step is hydrolysis, so we will add water, HOH, or you can also write it as H2O.
Right. Okay.
And 4 molecules of HOH will be there.
Correct.
So it will ultimately result into CH2OH plus aluminium hydroxide plus LiOH.
Okay, 4 molecules of RCH2OH will be formed.
Yeah. And now we shall see the learning part of this mechanism. The most important part on which basis we can solve the above question within a blank. The most important part is that the H minus attaches to C.
Yeah.
As you can see in the mechanism, this H minus is attaching over to C, and the hydroxyl of water means this H of water is attaching to the alcoholic group or the
oxygen atom.
The oxygen atom which was already existing.
Fine.
Therefore, a simple trick to remember that the hydrogen attached to carbon is from LiAlH4, and the hydrogen attached to the hydroxyl group will be from
the solvent which is used.
the solvent.
Okay.
So this is the most important part which we should learn from the mechanism.
Right.
So now let us proceed and see how we can solve our questions. In the first question, it's given LiLH4. We know that H minus. So therefore, and the second is D2O.
Okay.
So therefore, as we know, even the ester group will be also reduced by the same mechanism, and it will also follow the same steps.
Okay.
Therefore, the compound form will be as H is from LiLH4 and it is H, not a deuterated one, so here a normal hydrogen will be there, and here also a normal hydrogen will be there. And the second step is G2O.
Okay.
So, therefore, it will be OD and C, OD, H2 over here, plus we will be getting EtO, and it will also form EtOD.
Okay.
So this is the answer of the first. Now proceeding to the second question.
Fine.
We have seen here now it's LiAlDF4 and
The solvent is water in this case.
So again going by the same process, but this time we will be getting OH over here and again an OH over here plus EtOH and a D at this side because we have used LiAlD4.
Correct.
And finally, when we use NaBH4, we know what is the unique property of NaBH4, that it is a mild oxidizing agent.
Okay.
Reducing agent.
Reducing agent.
Reducing agent. So it will only reduce the carbonyl group, not the ester group.
Okay.
Hence, it will form so this is what our final answer is.
Okay, the ester group would remain intact in this case.
Because NaBH4 is a mild reducing agent.
Okay. So, as we saw in this problem, the reaction mechanism, knowing the reaction mechanism of how LiAlH4 with a combination of either H2 or DTO reduces an ester and a carbonyl group is very important. If you know the mechanism, you will be able to judge which hydride ion or which H plus ion gets attached to the carbon atom and at which particular position. So, this was it, and we'll move to the next question now. Okay, now we move to question number 2. This problem is based on reaction of a compound with Grignard reagent. So let us see how what is the reaction mechanism for this particular reaction.
In this reaction, first of all, R1, R2 and R3 depicts different alkyl groups.
Okay.
And as we know, this is Grignard reagent. So let us see how will it go.
Okay.
So we know by the basic mechanism that again the CO bond is polar and C has delta plus charge and oxygen has delta minus.
Right.
And we know that in RMGX, R is delta minus and Mg has delta plus, because Mg is a very high positive divalent atom,
right,
with oxidation state of plus 2,
X
is minus 1. So R also has to be a minus 1 oxidation state.
Okay.
Therefore it's very strong. So following the same concept, R will attack over here and MgX
will attack the oxygen atom.
Join here. So therefore we will get the compound as this. And as we proceed with hydrolysis,
yeah,
the compound we will get the compound to be R2OH.
Okay.
So was it not very easy question?
Yeah, it looks like very easy question in the first clue, but there could be a twist to this.
Yeah, the biggest twist is that this is one of the product which is going to be formed, and
Okay.
this is a minor product.
Okay.
Let me tell you. So don't be surprised, because here we are having a double bond also there in conjugation with C double bond O.
Okay.
So this is the whole reason we are getting one more product,
Okay.
and I will explain you why that product is more stable or why it is formed.
Okay.
The other product is like this: when R CH double bond CH, this one was R1, R2. Now due to resonance, this comes over here,
Okay.
and oxygen takes. What does this arrow signifies?
It signifies the shifting of electrons.
Shifting of electrons. So let me explain in some detail just once what is actually shifting.
Okay.
So in the C double bond O, from the pi bond of C double bond O, oxygen is taking the two lone pair,
Yeah.
the two electrons,
Okay.
because it's more electronegative than carbon. And so here the pi bond is shifting over here
Right.
due to resonance. Now we are adding over here R3 MgX. So we get over here R1 CH R3 single bond CH,
Okay.
double bond C, because the double bond was shifted due to resonance.
Correct.
Here we get an R, and here O MgX, because here O minus was there, so MgX, which was plus,
Yeah.
back over here.
And R3, which is negative, attaches the carbon which has lost the bond. Okay.
And when this is hydrolyzed, then we get RCH R3 CH R2 OH. And as you know that a double bond is in conjugation with lone pair with oxygen.
Okay.
Or is it just attached to the alpha carbon? And
Yeah.
that same carbon where OH group is attached.
Okay.
So in this case, usually the compound can undergo the process of tautomerization.
Okay.
So therefore, the compound will tautomerize and form and as you can see in this compound there is a conjugation and it's more substituted, whereas this compound doesn't have a conjugation.
Okay.
It's comparatively less substituted, therefore it is a major product, and we call this product, and it's thermodynamically also more stable, and it is also called as 1,4 addition product, and the above one is called as
1,2 addition.
product.
Okay. So as we have seen in this question, most of the students will commit this mistake. They will consider only the first product. They won't be aware of the splitting of bond, the shifting away of electrons, which takes place before the Grignard reagent is even added to the reagent. So it is very important to take everything into account while analyzing a reaction mechanism. We need to consider the most stable product which is formed in the end, and that will be our major product. The other product will also be formed, but in relatively lesser quantities.